When you look up at the night sky and spot the constellation Orion, there's one star that stands out in a particular way. Betelgeuse occupies a fascinating place in our cosmic neighborhood. Beyond its remarkable name, this star ranks among the nearest red supergiants we can observe. What does that mean exactly? While its surface temperature runs cooler than most stellar types, its sheer size defies imagination. Picture this: if Betelgeuse replaced our Sun, its outer layers would swallow everything inward from the asteroid belt. The star sits roughly 700 light-years distant, which places it considerably farther than the majority of stars visible to us. Yet its colossal dimensions make it the 10th brightest star we can see without optical aid, and it dominates the infrared spectrum. Finding it requires little effort. Look for Orion's left shoulder. When you do observe it against the darkness, you'll notice something immediately distinctive. Betelgeuse appears noticeably redder compared to neighboring stars, and it flickers more intensely than almost anything else in that region of sky. But there's another quality that sets this giant apart. Betelgeuse stands on the edge of a cataclysmic transformation. At any time, it could detonate as a supernova. That said, we need to clarify what astronomers mean by imminent. On the timescales relevant to stellar evolution, this explosion might still be 100,000 years away. What evidence supports this prediction? The answer lies in understanding how massive stars live and die. During what we call the main sequence phase, essentially the long adulthood of a star's existence, these enormous objects sustain themselves through nuclear fusion deep within their cores. Hydrogen atoms merge to form helium, and this process generates outward pressure that pushes back against gravity's relentless inward pull. It's a delicate balance. Gravity tries to crush the star into a tighter sphere, while fusion pressure resists that collapse. Eventually, though, the hydrogen supply in the core gets exhausted. Once converted entirely to helium, fusion halts. Without that outward force, gravity wins, and the core begins contracting. For stars with sufficient mass, this compression itself becomes the trigger for a new phase. The core grows hot and dense enough that helium fusion ignites, creating carbon and other heavier elements. This cycle continues, each time with a different fuel. Oxygen fuses, then neon. With every successive burning stage, the internal pressure causes the star's outer layers to swell dramatically. This is when the star enters its red supergiant phase, and by this point, the core has progressed to fusing elements into iron. Here's where the process reaches a wall. Red supergiants cannot fuse anything heavier than iron. When fusion finally ceases for good, nothing can counteract gravity any longer. The star undergoes total collapse, and that collapse produces a supernova. That's the stage Betelgeuse has reached. We're watching and waiting for this final gravitational failure. Whenever the explosion occurs, it will hurl the star's outer atmosphere across vast distances. From Earth, the event will dominate our sky for somewhere between 2 and 3 months before gradually fading. The distance protects us from any harmful effects, but the visual display will be extraordinary. Estimates suggest it might shine as brilliantly as a full moon, potentially visible even in broad daylight. Now, Betelgeuse has been making headlines for reasons beyond its inevitable fate. In 2009, astronomers noticed the star had shrunk by 15%. More recently, observations this year showed Betelgeuse dimming significantly. Scientists couldn't immediately explain the change. Naturally, speculation surged. Could this dimming signal the approach of that long-anticipated supernova? Unfortunately for those hoping for cosmic fireworks, the answer appears to be no. Fresh observations from the Hubble Space Telescope have revealed a different story. The star itself may not actually be dimming at all. Instead, dust that Betelgeuse ejected appears to have cooled and now blocks some of the light reaching us. Back in September of 2019, Hubble detected hot material streaming outward from the star's atmosphere. Over the following months, this material remained visible in the vicinity of the star. By December, dimming became apparent in Betelgeuse's southern hemisphere. The leading theory suggests that carbon heated to extreme temperatures rode along in this outflow. As this material traveled around the star, it expanded and consequently cooled. When it disappeared from view, it hadn't actually moved away from Betelgeuse. Rather, it passed across our line of sight. At the phenomenon's peak, Betelgeuse appeared roughly 2/3 dimmer than usual. Since April of 2020, however, Betelgeuse has returned to normal brightness. The obscuring cloud has either drifted clear of our sightline or dispersed entirely. Perhaps this wasn't the dramatic conclusion you anticipated. The supernova likely remains far in the future. But consider this perspective. Once the explosion happens, Betelgeuse will disappear from our sky forever. So the next time darkness falls on a clear evening, locate Orion overhead and take a moment to appreciate that red, twinkling star. It's Betelgeuse, and it won't be there indefinitely. Moving beyond individual stars, let's shift our attention to what remains after stellar explosions. The Hubble Space Telescope has compiled an archive on its website, a compressed file containing the 100 most remarkable images the observatory has captured. Over the next series of episodes, we'll examine these photographs individually and unpack what you're actually seeing. Some of these images demand considerable explanation to fully appreciate. This is episode 2, and several extraordinary sights await us. Image number 11 takes us to a structure known as the Spire. This formation consists of cold gas and dust, part of the larger Eagle Nebula, a region where stars are actively being born. The spire towers to a height of 9.5 light-years. Thousands of young, intensely hot stars located in a cluster just beyond the frame are actively eroding the structure. The hazy glow surrounding the spire is hydrogen gas being vaporized by ultraviolet radiation. The dark regions represent denser concentrations of gas that resist this erosion more effectively. This destructive process may simultaneously be creative. The bright, heated gas pushing against the darker, colder material generates pressure, and this pressure can trigger star formation. Stars also form within the tower itself, where dense pockets of gas collapse under their own gravity. The bumps visible on the surface might look modest in the image, but each one spans a volume equivalent to our entire solar system. These protostars will continue accumulating mass as long as surrounding gas remains available. The background displays more distant gas being illuminated. The blue coloration comes from ultraviolet light interacting with oxygen, while red indicates hydrogen. Image 12 carries us 210,000 light-years away to one of our satellite galaxies, the Small Magellanic Cloud. The region designated NGC 346 represents one of the most dynamic and intricately detailed stellar nurseries known to exist. At the heart of this region burns an intense cluster of brilliant stars, encircled by an irregular arch of dark, cool gas. Just as we saw in the previous image, ultraviolet light from these stars bombards the surrounding gas structure. You can observe the trails carved by stellar wind streaming past denser clumps of material. This particular star cluster also contains the single brightest star in the entire Small Magellanic Cloud. Number 13 brings us to the Crab Nebula. This nebula preserves the aftermath of a supernova explosion. Remarkably, we have historical documentation of this event. Ancient astronomers in Japan and China recorded observing this explosion in the year 1054. What fills your view here is the scattered remains of that star, composed primarily of hydrogen gas. If you look carefully at the center of this image, you can just barely discern a neutron star, the incredibly dense core left behind by the explosion. This object measures only 30 kilometers across, yet spins at the astonishing rate of 30 rotations per second. As it rotates, it projects two beams of high-energy X-rays into space. This is why the star appears to pulse when observed. This neutron star generates the bluish illumination permeating the nebula. Image 14 showcases the Orion Nebula. This particular image ranks among my personal favorites from Hubble's entire catalog. The colors are stunning, worthy of display in any art gallery. Beyond its beauty, there's remarkable complexity here. The Orion Nebula harbors approximately 3,000 stars, some of which remained undiscovered until this photograph revealed them. At the center of the brightest region, you'll find the 4 largest stars in the nebula arranged in a trapezoidal pattern. Appropriately, astronomers call them the trapezium. Surrounding these giants are extremely young stars that probably still retain their protoplanetary disks. You can see examples here. These disks of condensing gas may eventually coalesce into planetary systems in the far future. In the upper left portion, one star illuminates the dust around it, creating a region designated M43. We're looking at regions where dense pockets of gas manage to hold their ground against the erosive power of ultraviolet light, while other areas respond very differently to that same radiation. Some stars create visible bow shocks as they push back against the ferocious stellar wind unleashed by the most massive stars nearby. Over on the left side of the image, you can make out the boundary wall of the nebula itself. Something particularly fascinating shows up in the faint red points scattered throughout this scene. Those tiny specks of light are actually brown dwarfs, objects that some astronomers like to call failed stars. Brown dwarfs occupy an awkward middle ground in the cosmic hierarchy. Unlike our Sun, they never manage to ignite sustained nuclear fusion in their cores. Because of this fundamental limitation, they remain relatively cool, carry less mass, and shine far more dimly than true stars. And here's one more remarkable detail about the Orion Nebula. It holds the distinction of being the nearest star-forming region to our solar system, sitting at a distance of more than 1,300 light-years. Moving on to number 15, the Pinwheel Galaxy. We're taking a short break from nebulae now and shifting our attention to something considerably larger in scale. The pinwheel, which astronomers also catalog as Messier 101, belongs to a category known as Grand Design Spiral Galaxies. The image we have of this galaxy is enormous, allowing us to trace a detailed path from one edge clear across to the opposite side. In cosmic terms, this galaxy counts as a fairly close neighbor to our own, lying just 21 million light-years away. Its dimensions are also comparable to those of the Milky Way. What sets it apart are its very pronounced spiral arms and an unusually high concentration of regions where new stars are actively forming, visible in the areas where colors appear most vivid. This tells us that the pinwheel is an exceptionally active galaxy. The driving force behind all this activity comes from several sources, including stars that have exploded, gas heated to extreme temperatures, and material spiraling inward toward black holes. Number 16 brings us to the Cigar Galaxy, also cataloged as Messier 82. This spectacular starburst galaxy stands out because of the dramatic flame-like streams of red hydrogen gas being ejected from it. Stars are forming in this galaxy at a rate 10 times faster than what we observe happening inside our own Milky Way. Astronomers believe this furious pace of starbirth results from gravitational interactions with a close galactic neighbor known as Messier 81. The two galaxies are separated by only 300,000 light-years. Given their immense gravitational fields, they exert significant tidal effects on each other. Inside Messier 82 resides the brightest X-ray pulsar we've ever detected, designated Messier 82 X2. It appears as the large pink dot near the center of this image. This object has left astronomers genuinely puzzled because it's pumping out 100 times more X-ray radiation than something with its mass should theoretically be capable of producing. For perspective, consider X2's binary companion, Messier 82 X1, which shows up as the pink dot toward the lower right of X2. That companion is actually a black hole, yet surprisingly, it emits less X-ray radiation than the pulsar does. Number 17 is Cassiopeia A. What we're seeing here is the vibrant aftermath left behind by a star's supernova explosion. This remnant represents the youngest supernova remnant found within our galaxy, located just 11,000 light-years from us. The light from this explosion would have reached Earth roughly 300 years ago, yet curiously, no historical records document anyone observing it. One possible explanation is that the star had already shed its outer layers before the core exploded, and those ejected layers absorbed the light from the blast itself. However, the true reason remains somewhat mysterious. What's truly incredible is that the expanding shell from this explosion remains extraordinarily hot even now, reaching temperatures around 30 million degrees centigrade, and it continues racing outward at 6,000 kilometers per second. By this point, the shell has grown to approximately 10 light-years in diameter. Number 18 takes us to the Lobster Nebula. Here we have another stunning nebula located within the Milky Way, situated around 11,000 light-years from our position. This region also harbors numerous protostars, many of which are hidden behind dark disks and wrapped in cocoons of obscuring gas. At the heart of this nebula sits a star cluster known as Pismis 24. Astronomers initially thought that Pismis 24-1 was the most massive star ever recorded, weighing in at 300 times the mass of our Sun. Further investigation revealed, however, that this isn't a single star at all, but rather a multiple star system consisting of at least 3 separate stars, each carrying roughly 100 solar masses. Even with this revised understanding that reduces the individual stellar masses, these stars still rank among the most massive objects we know about in the universe. Number 19 is NGC 602. This image captures our attention not only because of its beautiful shapes and striking blues and oranges, but also because of the remarkable clarity of all the background galaxies visible behind it. The reason these distant galaxies appear so distinctly is that NGC 602 is located away from the center of the Small Magellanic Cloud, which means there aren't as many intervening stars to obstruct or distort our view. This positioning also makes the nebula itself considerably easier for astronomers to study in detail. At the center lies a cluster of young, brilliant stars that are actively eroding the surrounding dust walls. Finally, we arrive at number 20, NGC 1672. This is the final image for this episode. What we're observing here is a barred spiral galaxy. It features 2 prominent arms that extend away from the main body of the galaxy, with the arm on the left being significantly more defined than its counterpart. This galaxy actually possesses 4 arms in total. The remaining 2 are less clearly delineated and remain tucked within the inner regions of the galaxy. Interestingly, these spiral arms don't connect directly at the nucleus as you might expect. Instead, they attach at the ends of a straight bar of stars cutting through the galactic center. This distinctive structure is precisely why astronomers classify it as a barred spiral galaxy. Surrounding this central bar, the galaxy is experiencing what's called a starburst, an extraordinarily intense period of star formation. NGC 1672 lies at an impressive distance of 60 million light-years from Earth. Black holes represent one of the most mind-bending aspects of space. To begin with, they aren't actually physical objects in the conventional sense. Instead, they are the consequence of extreme warping of space-time itself. Because of this fundamental warping, genuinely strange phenomena begin occurring in their vicinity that will fundamentally alter your understanding of how the universe operates around you. Some of these effects are so bizarre that you might find them difficult to accept as real, were it not for the rigorous mathematics that support both their existence and their properties, along with the growing body of observational evidence from our own universe confirming that the mathematics is accurate. In this series, we'll be venturing into territory that seems almost impossible to explore. Come along on this journey as we work to comprehend the peculiar science behind how a black hole comes into being, what takes place in the regions surrounding it, and in the following episode, investigate what might actually permit an escape from what are arguably the most inescapable prisons found anywhere in existence. Black holes exist across a wide range of sizes. The smallest black hole we've observed carries approximately 3.8 times the mass of our Sun. At the opposite end of the spectrum, we encounter black holes that have existed since nearly the dawn of the universe itself. Black holes with masses reaching billions of times that of our Sun. These titans are not merely massive in terms of mass, they're also enormous in physical scale. The diameter of their event horizons would easily accommodate our entire solar system within them. The black holes forming in the present era represent the final stage in the life cycles of stars with particularly high mass. When such a star is born, it essentially maintains equilibrium through the interplay of 2 competing forces. The first force is gravity, which pulls all the star's mass inward toward its center. Deep within the star's core, hydrogen atoms are compressed against other hydrogen atoms with such tremendous force that they merge together to create a denser element, helium. This newly formed atomic configuration actually requires less energy to maintain than the 2 separate hydrogen atoms did previously. The surplus energy that remains gets expelled outward. This released energy constitutes the second force. It streams outward from the star's core in the form of heat and light, counterbalancing the inward crush of gravity. The star will maintain this relatively stable condition until fusion begins to falter as its hydrogen fuel supply dwindles. If the star possesses sufficient mass, once hydrogen starts running scarce, the star will begin fusing the newly created helium into even denser elements like carbon, neon, and eventually oxygen and silicon. But then, the star reaches iron fusion. The fundamental problem with iron is that fusing it doesn't result in any energy savings in its new configuration, which means there's no surplus energy available for release. Iron simply accumulates in the star's core, steadily increasing in quantity. Without energy pushing outward to resist gravity, the balance rapidly shifts. The energy released by this collapse is absolutely staggering. The intensity of this rebound depends entirely on how much mass the original star carried. Picture a massive hammer crashing down onto an anvil. The stellar material collapses inward toward the core with tremendous momentum, and when it strikes, the resulting shockwave rebounds outward. That explosive rebound is what we witness as a supernova. This violent release sends both matter and energy streaming across the cosmos in one of the most powerful explosions nature can produce. During this cataclysm, elements even heavier than iron are forged, stretching all the way up the periodic table to uranium. So what gets left behind after this cosmic fireworks display? The answer is not straightforward. It all comes down to mass. If the star's mass, and therefore the energy of that catastrophic implosion, falls below a certain threshold, what survives is something called a neutron star. These objects are astonishingly compact, barely reaching 25 kilometers across at their widest, yet they pack so much matter into that tiny volume that a single neutron star can equal the mass of 1,000,000 Earths. But if the original star was massive enough and the force of collapse correspondingly greater, then the laws of physics as we currently understand them simply give way. What emerges instead is a black hole. When you look at an image of a black hole, that dark sphere you see is not the black hole in its truest sense. Scientists believe the actual black hole itself is likely even smaller and denser than a neutron star. In fact, current theories suggest it might be infinitely small and infinitely dense, a point known as a singularity. This singularity generates forces so extreme they distort the very fabric of time and space. But here is the catch. We do not actually know what lies at the heart of a black hole, and the reason for our ignorance is something called the event horizon. We have understood since Newton that any object with mass exerts gravitational pull. But when Einstein published his theory of general relativity in 1915, a physicist named Carl Schwarzschild took Einstein's equations and reasoned that there could exist objects so extraordinarily massive that their gravity would be strong enough to trap light itself. And if even massless photons of light cannot escape, then nothing else can either. When you see a photograph of a black hole, you are not looking at the black hole proper. You are seeing the event horizon that surrounds it, the boundary where gravity becomes so overpowering that light can no longer break free. Beyond that line, there is only impenetrable darkness. The effects of a black hole extend beyond just space. They also profoundly affect time itself. According to Einstein, space and time are not separate entities, but are woven together into a single fabric called space-time, and mass warps this fabric. The singularity, with its infinitely concentrated mass, stretches space-time so dramatically that the event horizon also marks the point where time effectively stops. Inside the event horizon, the familiar concepts of space and time break down entirely. It becomes a realm where there is no meaningful notion of where or when. This creates a strange effect for anyone observing matter falling into a black hole from a safe distance. To that outside observer, as an object moves closer to the black hole, it appears to slow down. Just before it reaches the event horizon, it seems to freeze in place. This orbital dance allowed scientists to calculate the mass of the invisible companion. What they found was startling. This unseen object weighed 15 times as much as our Sun. Since the most massive neutron stars cannot exceed about 3 solar masses, scientists concluded they were almost certainly looking at the first confirmed black hole. Since that discovery, we have identified many more black holes. Supermassive ones appear to lurk at the centers of galaxies, and we have even captured images of some, showing dark silhouettes against the brilliant swirling rings of material that orbit and spiral into them, known as accretion disks. This is also how black holes can still be detected through X-ray emissions. While black holes themselves cannot emit visible electromagnetic radiation, the X-rays associated with them actually come from their accretion disks. As matter falls inward, it accelerates and collides with other material, generating intense friction that heats the infalling gas and dust to temperatures reaching millions of degrees Celsius. This superheated material then radiates X-rays before crossing the event horizon. Black holes that lack infalling matter, on the other hand, are essentially invisible, with no luminous accretion disk to betray their presence. The study of black holes remains an active and evolving area of physics, with many unanswered questions still on the table. Based on what we understand so far, you might wonder whether a black hole could ever cease to be a black hole, or whether it will simply continue growing indefinitely until all matter and radiation in the universe have been consumed. At first glance, perpetual growth seems inevitable. However, in 1974, physicist Stephen Hawking published a paper titled Black Hole Explosions, in which he proposed that there actually is a mechanism by which energy, and therefore mass, could escape from a black hole. But understanding why requires us to venture into some truly bizarre territory. We need to explore certain principles of quantum mechanics. Before we go there, though, let me pose a challenging question. What exactly is nothing? Imagine a region of space that contains absolutely nothing. No particles of dust, not even a stray photon passing through. By all appearances, nothing whatsoever exists in that volume. But is there truly, fundamentally nothing there? It turns out something essential does exist in that space, and we can infer this from the behavior of light passing through it. If you know anything about the nature of light, you know that light consists of oscillating waves of electric and magnetic fields that propagate forward in a straight line. But consider that word, wave. A wave in the ocean is energy moving through water. If you track a single water molecule, it is not actually traveling toward the shore. It mostly moves in a small circular or elliptical path. Yet because it transfers energy to neighboring molecules, the wave itself progresses steadily forward until it breaks on the beach. Similarly, a sound wave travels by transferring energy from one air molecule to the next. Each individual particle vibrates only slightly, becoming energized and then passing that energy along to the next particle in the sequence. But in our hypothetical vacuum of space, where there is supposedly nothing at all, where a photon is traveling as a wave, have you ever paused to ask what exactly is doing the waving? This points to a fundamental something that exists even in the absence of matter or radiation, an underlying fabric that constitutes reality itself. Quantum physicists refer to this something as a quantum field. Quantum fields are difficult concepts to fully grasp, but they are absolutely essential when it comes to understanding the ultimate fate of black holes. This is a topic I hope you will explore with me in the next episode, where I will delve into this in greater depth and hopefully in a way that does not require an advanced degree in astrophysics. Have you ever imagined what it would be like to witness a supernova up close? While we are not expecting one in our immediate cosmic neighborhood anytime soon, you will have the opportunity to observe something that is arguably the next best thing, the eruption of the Blaze star. And remarkably, this star just keeps exploding. In May of 1866, on a partly overcast spring evening in Western Ireland, an amateur astronomer named John Birmingham was making his way home in the darkness just before midnight. He walked slowly at times, pausing now and then to gaze upward at the stars above. With keen attention, he swept his gaze across the darkness overhead, searching for the patterns of stars he knew by heart from years of observation. His eyes moved steadily through the familiar territory of the sky until they arrived at the Northern Crown. Then he froze. Right there in that constellation he could trace from memory, a bright star now shone where none had existed before. What he had just witnessed was a recurring nova within the binary star system T Coronae Borealis, often called the Blaze star. This kind of explosive celestial phenomenon unfolds only once across the span of a human life. The discovery would eventually transform how astronomers understood nova events and fundamentally influence the direction of stellar research for generations to come. For anyone living in 2024, we stand on the edge of an extraordinary moment. We will get to see the very same recurring nova outburst that held Birmingham spellbound over a century and a half ago on that crisp spring evening in Ireland. You will not need a telescope. You will not need specialized gear of any kind. So why does this happen again, and when should we expect it? The name blaze star might give the impression of a single object, but the reality involves two stars bound together in mutual orbit. The nova explosion we observe roughly every 80 years is a direct consequence of how these two stars interact. In truth, around half of all the stars visible in our sky are not alone. They exist as part of multiple star systems. The two stars that make up the blaze star binary both began their existence as ordinary mid-sized stars, much like our Sun, yet each has reached a vastly different point in its evolutionary journey. Stars of small to medium mass typically progress along the same evolutionary track our Sun follows. Our Sun sits at 4.6 billion years old, placing it comfortably in the middle of its lifespan as an average star. In another 5 billion years, it will exhaust its hydrogen supply and start fusing heavier elements, swelling outward into a red giant potentially large enough to consume Mercury, Venus, and perhaps even our own planet. Once the red giant burns through whatever fuel remains, somewhere between 5 and 10 billion years from now, it will shed its outer layers and leave behind a glowing shell of gas encircling a white dwarf. This white dwarf represents what is left, an incredibly dense and compact core of what was once a giant star. White dwarfs earn the nickname dead stars because they have depleted all their fuel. From that point forward, they will spend the next 10 trillion years gradually losing heat until they emit neither warmth nor light. Both members of the blaze star binary are average-sized stars following the same path, but they have traveled further down that road than our Sun has. This difference in their life stages is precisely what drives the recurring nova we will observe in 2024. Everything hinges on the dynamic between these two stars. One has become a red giant, the other has already collapsed into a white dwarf. As the red giant heats up and its outer layers begin to expand, the intense gravitational force of the nearby white dwarf continuously pulls hydrogen away from it. Over long stretches of time, the white dwarf accumulates this stolen material on its surface, functioning somewhat like a cosmic vacuum cleaner. This accumulation generates mounting pressure and rising temperature. Eventually, the buildup crosses a threshold and triggers a thermonuclear explosion that violently expels all the accumulated matter. Think of the white dwarf as resembling a party popper. You pull the string tighter and tighter, steadily increasing the tension. At some point, you pull too hard and it bursts, scattering confetti in every direction. The pressure and heat gathering on the surface of the blaze star's white dwarf work in much the same way until conditions reach a breaking point. What follows is a nova explosion powerful enough to make the blaze star appear roughly 1,500 times brighter than it normally does, an event that occurs approximately once every 80 years as observed from Earth, 3,000 light-years distant. How does this differ from the more widely known supernovas? While the blaze star does undergo a massive explosion with each nova, classified as a classic nova, the white dwarf itself survives intact. The explosion simply blows away the material gathered from the companion star whenever the pressure and heat become unbearable. Because the system lies close enough to us, we witness a dramatic shift in its brightness from our vantage point on Earth. For a solitary star to obliterate itself at the end of its existence through a spectacular supernova that can shine millions of times brighter than the blaze nova, it must begin with more than 8 times the mass of our Sun, far more massive than either star in the blaze system. The nearest star currently on course toward a supernova explosion in what astronomers call the near future, a star that frequently ranks among the 10 brightest objects in our night sky despite sitting 640 light-years away. When scientists say the near future, they mean from a cosmic standpoint. There is no need for alarm. Researchers do not anticipate this star going supernova for tens of thousands of years. In the vast timescale of the universe, that qualifies as just around the corner. In human terms, it remains impossibly distant. Yet for a moment, picture the breathtaking spectacle anyone on Earth would see if Betelgeuse were to explode as a supernova. Following the initial blast, the star would shine as brilliantly as a full moon and stay visible throughout daylight hours. What an incredible sight that would be. That said, while extraordinarily uncommon, Betelgeuse would not mark the first time humanity has observed a supernova, and the blaze star is far from the only nova in recent centuries visible without optical aid. The earliest documented supernova, now designated SN 185, comes from Chinese astronomers in the year 185, when they noted what they called a guest star appearing in the night sky for an astonishing 8 months. Modern astronomers have located the remnants of that explosion, confirming it was indeed a supernova. Only a small number of supernovas have been visible to the naked eye throughout recorded history. One of the most celebrated examples, and the most recent, occurred in 1604, when the German astronomer Johannes Kepler recorded a supernova so luminous that people could observe it in broad daylight. What we will witness in 2024 is anticipated to be among the brightest classic novas of this century. Much like a supernova, this qualifies as a rare and significant event. Classic novas visible to the naked eye happen with relative frequency, at least when compared to supernovas. Yet despite these classic novas appearing in our night sky roughly once every year or two, they rarely shine brightly enough for someone without training or equipment to detect them. The blaze star, however, is expected to become one of the most luminous classic novas to grace our night sky in nearly 50 years. In the field of astronomy, the brightness of a star as perceived from Earth can be quantified using a scale called apparent magnitude. The lower the magnitude number, the brighter the star appears. A star with a magnitude of 0 outshines a star with a magnitude of 1. A star with a magnitude of 1 appears brighter than one with a magnitude of 2, and the pattern continues. Generally, a star or planet needs an apparent magnitude of around 6.5 or lower to be visible to the naked eye on the darkest nights. To put this in context, the 7 stars forming the Ursa Major constellation, commonly known as the Big Dipper, range in apparent magnitude from the faintest at 4.8 to the brightest at 1.7. The most luminous star in the night sky is Sirius, registering a magnitude of -1.44, while our Sun during the day measures a magnitude of -26.5. Yes, the apparent magnitude scale extends into negative values. The blaze star typically has a magnitude of 10, rendering it invisible to the naked eye from Earth. But during the nova explosion that occurs every 80 years, this star reaches a peak magnitude somewhere between 3 and 2nd. It makes the system suddenly visible, transforming it from virtual invisibility into one of the most luminous points in the entire night sky. The word nova itself derives from Latin, where it simply means new. Before the invention of telescopes, imagine the astonishment people must have felt witnessing what appeared to be a brand new star materializing in the heavens without warning. A more recent example is Nova Centauri 2013, which caught astronomers off guard by becoming one of the most brilliant novae seen in more than 100 years, hitting a peak brightness of magnitude 3.3. When the blaze star last underwent a nova eruption back in 1946, it climbed to magnitude 3. This time around, though, astronomers are anticipating an even more spectacular display. The blaze star could potentially reach magnitude 2 at its brightest, putting it on par with Polaris, the North Star, which shines at magnitude 1.97. The spectacle, however, will be fleeting. After the nova detonates, the blaze star might remain visible without optical aid for only several days, perhaps stretching to a week, before dimming once again into obscurity. There is no way to pinpoint the exact moment of eruption, but researchers believe it could occur at any time as we move deeper into the second half of 2024. Stay tuned to astronomical news and keep watch on the heavens to catch the moment this nova ignites. If you want to locate the blaze star once it flares up, begin by identifying the constellations Hercules and Lyra, which has a distinctive kite-like shape. The blaze star sits within a small, delicate constellation known as Coronae Borealis, the Northern Crown, nestled between these two more prominent star patterns. If you trace the arc of the Northern Crown starting from the direction of Boötes and moving toward the side nearest Hercules, The blaze star should emerge just beneath the final star in that semicircular crown. For those with access to a quality amateur telescope or a nearby observatory, there may even be a chance to observe this binary system before the nova erupts, allowing for a true before and after comparison. These novae serve as vivid reminders that stars, which often seem timeless and immutable, actually undergo remarkable life cycles filled with sudden transformations and violent outbursts resembling celestial fireworks. Rare and awe-inspiring. Every nova offers astronomers an invaluable chance to collect observational data that deepens our knowledge of how stars evolve, how binary systems behave, and the mechanics behind explosive stellar events. This particular nova will rank among the most thrilling astronomical phenomena any of us will witness during our lives. So keep your gaze trained on the night sky, and perhaps take a moment to feel fortunate to be alive at this exact moment in history, able to witness such a cosmic event unfold from our vantage point here on Earth. Have you ever observed a nova without any equipment? Are you making any special preparations for when the blaze star nova finally erupts? Until next time, keep looking up and stay curious.